Hello, everyone, and welcome back to Computer Organization and Programming. And today we're gonna focus on the basic concepts, and that's what we call Chapter 1. So just gonna look at the basic idea of the core concepts. Okay, so what's an assembly language, and where assembly language actually fits in terms of programming languages in general. And we're going to hopefully look into the, after we cover that, we're going to look into the binary and hexadecimal data representation. And this is going to be a very important topic. This part is going to go with you from this chapter to the end of the semester, okay? So this is going to be very important. And we're going to also cover what is signed and unsigned integer arithmetic. And that's, again, chapter 2, 3, 4, 5, and except for the floating point, it's going to be mainly based on these two core concepts. So they are going to be very important. During the regular semester, I usually cover the Boolean logic, but you guys know what it is, just refer to the book. And try to look for an example for multiplexers and adders, so that way you will see how those Boolean logics are actually implemented or used to create those components. So since the time is really tight, I just removed them. So I can keep the slides after I record this video, just in case if you want to look at them. But I would not test you in terms of testing, but if in terms of knowledge, they're going to help you a lot. Okay. So let's get started. So we're going to look at the first part, so the assembly language. And once we do that, we're going to focus on the virtual machine concept. So virtual machine, it's not anything to do with, it has nothing to do with anything that you know about real virtual machines. This is just data, it's a model to think about how machine language and assembly and the hardware interacts with each other and the operating system. Okay. So let's focus on the assembly for now. So what is it that we're going to learn in this class in terms of assembly language? Definitely this week you're going to install Visual Studio. So that is going to be the software like Microsoft Visual Studio. And if you have a Windows machine, life is going to be way easier. If you don't, then you're going to find the slides in which you will learn how to install how to install Visual Studio on top of Mac. And something that I want to warn you about right now, you might find a Microsoft Visual Studio for Mac. That is not something that we're going to use in this class. The Microsoft Visual Studio for Mac, it is mainly made for C# and ASP.NET. It is not for us, okay? So we need C++, and because C++ has a compiler, and part of every C or C++ compilers is going to be an assembler. So that's what we're going to use. All right. So please follow the slides in terms of installing Microsoft Visual Studio on Mac. Try not to install directly Microsoft Visual Studio on top of Mac without having a virtual machine. All right. And we're going to focus mainly on 32-bit programming. And that is going to be very important to know because we have 64-bit programming. This is something that we should really go to and convert the class into 64-bit, but for some logistic reasons, I couldn't do that for the past year and a half. And we also have 128, and we also have 56-bit programming. So these are not going to be things that we're going to cover. So we're going to focus mainly on the 32-bit programming. You wouldn't know what I mean by the 32-bit. You might scratching your head right now and you say, what is he talking about when he say 32-bit? That's going to be very handy very soon, okay? And we're going to mainly focus on x86. This is the family that we're going to study in details, okay? So this is going to be Intel x86 assembly, okay? So that is the environment. So this is what we're going to do in terms of assembly. And there is this website, the author of the book, and it has a lot of information in there. It has some examples, have some exercises, so it is worth visiting and playing with. So the first thing that you need to really keep in mind that when you talk about assembly language, it's going to be the relationship between, I call them the utilities, because we have assemblers, linkers, and debuggers, right? So if you have a source code, so it happens that the source code right now is in assembly. So you are moving a memory reference, which is A, to EAX, which is a register. You multiply A with B, and the result is going to be stored in a register. We will understand what a register is, but in general, a register is inside the microprocessor. This is your microprocessor. This is the main memory. Okay, that is the main memory. So the registers are inside the microprocessor. A is in this memory. So EAX is going to be here. The A is going to be in the main memory. So we are moving from memory into a register. You see what I'm talking about? So when we move things, those data are stored in terms of bits, right? Is it stored in terms of 8-bit, 16-bit, 32-bit? That's what I said, 32-bit. We're going to focus mainly on 32-bit programming, okay? So we're going to talk about this in more details. But once we do that, then EAX right here is going to store the result. We're going to add C, which is another space in the main memory. We're going to add this to EAX. So EAX now has a new value in there. And then we're going to print it out. So this is the source code. You know, this is a human type, right? It's a human-like language, right? So in order to translate this, that is your source file, you have to have Microsoft Visual Studio, okay? So you need to have that, Microsoft Visual Studio, all right? So if you have Microsoft Visual Studio, that means you have the editor. So with the help of the editor, right? With the help of the editor, you're gonna write this code. And then you're gonna do what? You have to save it. Once you save it, you have the source file, okay? So if you have the source file inside Microsoft Visual Studio, there's an assembler, right? So this assembler is gonna translate the source file into what? Into an objective file. Okay, so this objective file, it's like another translation. So now we're gonna, like, it's an intermediate translation before we go to the machine language. All right, so why are we doing this? Why are we doing the objective file in here? So that is the idea behind designing a compiler. So you cannot translate from the source code directly to the machine. So it has to go through phases, okay? So it has to go through phases, and this is one of them. So once we have the objective file, that means these are gonna be translated into a form that is a little bit in between. It's close to the human and a little bit close to the machine, okay? But it's not yet a machine language. So then we're gonna need a linker. So this linker is gonna, because the linker requires the source file to be in a specific format. That is why the assembler produces the objective file. So the assembler prepares the source file into a format that is going to be an input to the linker. So the linker is going to take these object file in addition to what? To the library. What is a library? This is write-len in here. Is write-len an instruction? No. Add is an instruction. Mul is an instruction. Move is an instruction. But write-len is a function, a procedure, a method. You can name it whatever. And this write-len is actually a program. You're just calling it from your own program, right? Excuse me. So you're calling this program, which is write-len, but this program is not something that you written, right? So you have to link this program. That's the idea of the linker. So you have to link this write-len program. So the linker is going to go and ask for the source of for the write-len, because it's a file that has the source file, and it's going to link it along with your program. And then it's going to produce what's going to produce the executable. So this is the executable. That is the machine language. And if you remember, we talked about ISA in the big picture, the instruction set architecture. I say the machine language. That is the machine language for Intel. Okay. So sometimes you want to run your program and you want to control it. And if you want to run the program and you have it under control, and you want to interrupt the program at a specific points, you're going to create a breakpoints. You're going to say, stop the execution here, continue, go over this statement, do not execute it. If you want to have those kind of control, you need a debugger. So that is the whole idea of the debugger. So when you execute the file, when you have the executable file, that doesn't mean you executed the file. You just have the executable file. If you double click on this, it's going to be executed by the operating system. If you load the executable using the debugger, then that is when you're going to execute the program under the control of the debugger. Okay, so the debugger is going to give you the giving you the ability to to execute the code under a specific control, because the debugger is a utility. You can create a breakpoints right there. You can stop the execution. You can skip some statements, you know. So you can go and execute a loop step by step. You can go within the procedure and you can execute it step by step. So you need a debugger. So you're gonna learn a debugger in this class as well. So in this class, you will learn the assembler and you will learn a debugger, which is Microsoft both. They're going to be Microsoft assembly. Okay. So that is part of what is the big picture of an assembly language. So we know what it is. So you need an assembler, you need a linker, and you need a debugger, right, in order to really understand an assembly language. All right. So again, as I said, the assembly language is a way to unlock the hardware. So you are not really learning a language, at least from my perspective. It's you are using the language to understand the hardware. All right. So here, if you look at the difference between assembly language and traditional languages like C or Java. So if you see this question right here, how does assembly language relate to machine language, right? It's one-to-one because every instruction has an instruction set, equivalent instruction set, right? So if you look at the C and the assembly language right here, this is going to be what? It is going to be one-to-many, okay? Because you are writing at a high-level language, right? So if you write at a high-level language, you are abstracting, you are hiding a lot of details, okay? So this is straightforward in one line. You say add 4 and multiply by 3. So if you, in order to do this, you need 1, 2, 3, 4, 5 lines. Don't worry about it if it looks like a little bit gibberish for you. So it's going to be very clear very soon. All right. So this is very important. You need to understand that that the high-level language relationship with an assembly language is not one-to-one. It's one-to-many. And if you want to take this now to a machine language, right? So every line is going to has a specific machine language, right? Or specific instruction set, right? So that means that the high-level language the relation between the high-level languages and the machine language is going to be one-to-many. All right, so just keep that in mind. So is assembly language portable? So if you translate this, because this is not going to be executed, right? You have to translate C or C++. That's not the case for Java, but at least for C. You have to translate them into an assembly using the compiler. And then you have to take the assembly language and translate it to the machine language, which is here, right? Using the assembler. Okay? So once you do that, you're going to have, if you notice right here, you're going to have what? You're going to have the executable, if you notice right here, right? So that's going to be the executable. So once you have the executable right there, okay, is that executable portable? No, it's not portable because the assembly language or the assembler and plus the linker, right? Because the linker produced the executable, right? They're going to produce an executable. Is this executable portable? No. What I mean by portable, if this was made for Intel, right? And you want to take this and execute it in ARM, that's not portable. It's not going to go and execute right there. Why? Because the instruction set, remember when I talked about this statement? Right? And then I ask you, is this something you understand? And you definitely say, no, I don't. So if I say, okay, I will translate this into this, right? You know, assembly, definitely you're gonna interact with this statement, right, guys? So this is an instruction set, right? And this is a different instruction set. So the assembly, along with the linker, they create an executable file based on a specific instruction set. So these instruction set for Intel, if you want to take them and execute them there, they are not going to work. So that's why the executable here is not portable. So the assembly language is not portable. All right. So just keep that in mind. Okay. No, and we know why, right? Because of the instruction set. Okay, because each machine is going to be, each assembler is going to translate into a specific instruction set, and that's going to be based on the underlying hardware. Okay, we're going to learn later that even though the instruction set is okay, but the operating system is different, it's not going to be portable. It's not only the instruction set that's the bottom line, but the instruction set is the core thing, okay? And then if you want to know the best way to use the assembly language, okay, it's definitely not these 2 points, right? You're not going to use assembly language to write a bank system. It's possible, but it's going to take 2 years to do it. So productivity, I call it PP, productivity and performance, okay? So in terms of productivity, okay, so that is, especially for a business, you need to get it done within 6 months, then that's going to be impossible. So that's going to hurt what? Productivity. But if you want to do it, I said, I don't care. I will do it in 2 months. That's in 2 years. That's fine, because I want performance. That's great, because your program is going to be really fast, faster than Java. Because Java's productivity-wise is way easier, and development-wise is way easier, because you are using OOPs and you're writing things at a high level. But if you want to do that in assembly, it is going to be way harder. Okay. So assembly is better, is used when you're dealing with hardware device drivers, or you're going to do embedded system or computer games. So if you know assembly, computer games, and then I will add also security, reverse engineering. So these are the parts when you need the assembly language. Okay. So this is just a simple question. Is the assembly language for x86 processor the same as those for, like says Motorola or ARM or whatever? Definitely you're going to say no, right? And you know, because every architecture has its own instruction set, right? So this is what we call the ISA. So the instruction set for x86 is different from the instruction set of Motorola or ARM assembly. Okay, so these are like the 2 programs. Let me see if I can erase this. Okay, let's just say erase this part. Okay, and back right here, this is the ARM assembly and this is the Intel assembly. So these are 2 different assembly language. This is an ASM and this is another assembly language, right? These are 2 different in terms of syntax, and they're gonna use the assembler to translate into a specific machine language. So this machine language and this machine language, when I say machine language, I'm talking about instruction set. So the instruction set right here is going to be definitely different. So this move is going to be translated into a different move from here. Though at the high level, they both look the same for you, but for the microprocessor, for the hardware, right here, they are completely different. So that's again, we said, is assembly language a portable program? It's not portable because it's committed or is translated to a specific machine. Okay, so with that, hopefully now you understand what you need to write an assembly language program, where assembly language actually fits in terms of high level and low level. So you need to understand that machine language is mainly for hardware. When you are writing a code close to the hardware, like Internet of Things, embedded systems, hardware drivers, then or maybe games, or maybe as long as the performance is important or the security is important, you need to go to the assembly language. Okay, so, and as I said, in this class, we are just taking assembly language just to unlock the underlying hardware. All right, and if that is clear in your mind, and now you understand that machine language is not portable, and you understand how an assembly code is going to be translated into a machine language or into a specific instruction set. So you looked at the assembler, linker, and the debugger. Okay, so now we're going to focus mainly on the virtual machine concept. So I hate the name. This is used by the book, but it is not the virtual machine. It's just like a model to understand the relationship between assembly language and the hardware. Okay, so let's just get that straightforward. Okay, so if you look at the virtual machine, this is what the virtual machine is. So this is just a model, and in this model, this is going to be your hardware. Okay, and this is going to be your software, and this is going to be the instruction set. This is the interface, if you remember. So this is going to be the interface. So if you write a code in a high-level language or an assembly language, you're definitely going to need an operating system. Why? Because remember, linkers and assemblers, okay, and debuggers, okay, just keep that in mind. They cannot work by themselves. They believe that they have a layer beneath them because they cannot operate the machine. They assume that the machine is operated or controlled by a software, which is an operating system right here. So the operating system is going to take whatever the execute, because if you are writing an assembly code, you need an editor, right, guys? Because out of the editor, I'm sorry, okay? If you have an editor right here, and then you write the code, and then you read an assembler, right? So this is number one you need, this is number two, and then you need the linker, and the debugger is optional, okay? So in order to do this, right, remember we have a write-len statement, we say call write-len. So this is part of the operating system. So everything that you're going to use at the assembly language level or at the high level language level, it's going to require the operating system service. So the operating system has to be there. Okay, so the whole idea here is we're going to explain how the computer's hardware and software are related. So this is the hardware, this is the software. So this is, in terms of software, I would say the operating system. Okay, this part is the operating system, and this is the languages part. Okay, so we are right here. So in terms of assembly language, we are using Microsoft Windows, right? Or maybe Mac. If you are using your Mac, in fact, you're using Microsoft Windows because you're going to create a virtual machine, right? And then you're going to have also the operating system has to be right there, right? And this operating system knows how to communicate with the instruction sets. And the instruction sets knows how to control the microarchitecture. And the microarchitecture is going to operate the underlying logics, which is what we call right here the digital logic. Okay, so the question here is going to be, why don't we just write our programs right away using the instruction sets? That's going to be difficult, right? It's very hard. Okay, it's difficult to write programs in machine language because you have to be really good at writing zeros and ones, and we are not good at remembering numbers. So we use symbols, and that's why we have our own language. And even in assembly language itself, you see that we are using add and we are using move, so it's very close to the human language. Before this assembly, it used to be numbers. That's why we moved from a number a representation into a symbols. And then in the high level language, that's when we moved into using words or a human-like language. So the bottom line here, we cannot write into this, using the machine language. So that is why we are forced to create a new language, which is an assembly language. And after that, on top of the assembly, we created a high level language. Okay, guys? All right, so if you start at the level number 5 here, you write something in C and Java or in Visual Basic. So if you want to do this, you have to use a compiler. Okay, and that compiler is going to translate into an assembly if you are using C or C++. If you are using Java, Java does not actually convert directly into an assembly. It's going to create an intermediate file. Okay, and even Visual Basics, these are two scripting languages, Java and Visual Basic. So they have to create into an intermediate first, and then once they know what is the underlying hardware, they're going to translate into an assembly. But at the end, they're going to translate into an assembly right away. Okay, so here I'm talking about C or C++. So it's going to translate into an assembly language, right? So that is the first thing that we're going to do. So if you look at it right here, this is your high-level program. You write it in a high-level language, right? Then the C compiler is going to translate this into what? Into an assembly code. Okay, so now you are at the assembly level, all right? And if you are using the assembly is going to use the assembler, and the assembler is going to produce the objective file, remember that? And then the objective file is going to be the input to the linker, and the linker is going to produce the executable. Do you see the idea right now? Okay. These are basic concepts that you should have in mind. This is the assembly language. This is what we talked about right now. And this assembly language, again, is going to be translated using an assembler, right? So it's going to be translated using an assembler into an instruction sets, but that's going to require what? That's going to require the linker. Keep that in mind. So the assembler gives you the objective file. The objective files are going to be an input to the linker, and the linker is going to produce the instruction set. Okay, so this is exactly what the level 4 is all about. So if you have call functions for the operating system, like the one right here, so the linker is going to go and link this, and then Once we do that, we have a complete objective file in the library, and then we're going to produce the executable file. Okay, and once we produce the executable file, that means we are having the instruction set. So instruction set architecture is similar to what? To the machine language. So they mean almost the same. They have some differences, but I'm not going to talk about them right now. So this is the operating system. Why we need the operating system? Definitely because when, as I said, the programming language cannot operate a machine. So you need a system or a software that operates the machine. And it provided services. This is one of the services, because if you don't have the right len, you have to write the program yourself. So that is going to be like when you have a flat file. Okay, so when, let's say you have a problem with your while driving, and then you have a problem with one of the wheels, right? It went flat for some reason, right? Are you gonna create a new one, call your family and maybe your whole community, and you sit down and you create a wheel? Just maybe it's gonna take you a couple of days to do that, or maybe a month, I don't know. Is that better, or you're just gonna go and purchase a new one? So that's the idea of the surface. The operating system provides you a surface with writing a content in the screen, because that's a long story. That's why those companies, they make money, because they save you time and they provide you with services, right? So if you have a flat tire, you're not going to go and create a new one. You're just going to go and purchase a new one. The same thing, if you want to print something on the screen, you can do that if you want. This is a good exercise, but you cannot do it all the time, right? And you have different monitors, you have different settings, you have different monitor cards, and you need to understand all of those, right? Save yourself some time and call the operating system service, which is RightLen. So you need to have the operating system. Without it, it's impossible. And once you do that, then you're going to go to the, that's the interface between this part, which is the software, I call it, and programming languages, and the hardware. So everything that you're going to do in terms of the software, it has to go to this level. If you need the machine to execute or to run whatever you have in your program, okay? So once you do that, then now we are getting into the very pure hardware. Okay, so the instruction set, each instruction knows what microarchitecture that needs to connect with. Okay, so let's say if we want to add, we are going to go to a microarchitecture, a circuits we call what? Adder. And the adder now is going to talk or communicate with the dumb hardware, which is the digital logics. And the digital logics are going to go and actually do the real mechanics of adding two numbers. Okay, so this is actually the digital hardware. All right, so if you want to go from level 2, you need to go to the level 0. That's when you're going to have the digital logic. That's what is really actually the mechanics and the real computational power. It actually happens in this part. Okay, so it's gonna interprets the instructions that are written at the high level, and then is gonna map them to the microarchitecture, which is in turn is gonna map those instructions into the level 0. So the microarchitecture right here is gonna be whatever you have in this level 0. It is going to be the CPU, it is going to be the memory, it's going to be the system bus, it's going to be the gates, so it's going to be the transistors. These are all going to be in the digital logics. So the microarchitecture right here, as I said, it's just going to be the one that takes the pure software instructions and then is going to map them to the underlying digital logics, which is what we call the hardware components, like the CPU, the memory, the system bus, and so on and so forth. Okay, so this is mainly the idea of the virtual machine. So hopefully now you understand that this is the hardware, and this is the software right here, and this is the interface in between. Okay, so in order to write a program that adds speed to A, you have to write this using a language, and you need the operating system that operates your machine. And then now you need the utilities, which is the editors, and then the assembler, right? And then the linker, and hopefully maybe you're gonna need the debugger, right? So these are the utilities that you're gonna use either at the high level or assembly language level. and you're gonna use them to write this program, and then translate it into an instruction set. Once you do it and you translate it into an instruction set or instruction sets, then the instruction sets, they're gonna communicate with the microcontrollers. So the microcontrollers are the ones that they directly communicates with the underlying hardware. Okay? So this is exactly what I was talking about right now. So this is a human language, right? This is a human language. So you say display the sum of A times B plus C. So if you use like a machine, right here, I would say high level language. So this is a human. Okay, let me say it a human in this way so you're not gonna confuse the terms. This is a high level language. So in C++, you're gonna write this in one line. You multiply and then you add, excuse me. Okay, and then the compiler is going to translate this into an assembly, and the assembler and the linker, they're going to translate this into a machine language, which is the instruction set. Okay. All right, so now we understand what is a machine language, what we need, and we understand the fundamental of at least how the software interacts with the hardware throughout the instruction sets, and that is the virtual machine. Now we're gonna get our hands a little bit dirty, and then we're gonna move into the data representation. This is a very interesting topic. It is challenging too, so just bear with me, okay? But I believe that challenging, when I say challenging, it means that you have already been through this and the introduction to computing. If you find it still challenging, just go back to those courses and try to look at the fundamentals. Otherwise, just there are a lot of YouTube videos that you can use to use as a reference to review or to refresh your memory in terms of data representation. But I cannot emphasize this more. This is a very important component. It's going to go with you, as I said, from now until the end of the semester. Okay, so we're going to focus on the binaries. Binaries are the machine language, so you need to master the binaries. Okay, what are they, how to convert them, how to convert to binary from binary, and so on and so forth. Okay, so when we look at the numbering system, okay, so we have either binary, octal, decimal, and hexadecimal. So in this class, we're going to focus on those, okay? Binary, decimal, and hexadecimal. This is our strength, right? We know decimal very well. Okay, so if we know decimal, how can we go from decimal to binary, from decimal to hexadecimal? But again, we are dealing with the machine, so we don't care much about the decimal. That's the human machine numbering system. We're focusing on the machine numbering system. So you might say, why do I need to learn hexadecimal? It's also heavily used, especially in addressing the memory. So it's also, again, this is also a machine language as well. Hexadecimal is well known. So you will see that when you start playing with the debuggers, and once you see the exercises and everything, you will understand that the importance of those. Okay. So as I said, again, everything, if you want to examine a register or a memory, you're going to see things on binary. Okay, I'm not talking about Visual Studio. In Visual Studio, you can control the representation of the numbers. So you can make all of them in decimal, and life is easy. But in case if you are going to use Linux, or you go to the network administrations, or you're going to go to the security field, then you're going to use tools that they don't have the luxury that Microsoft have. Okay, so you're gonna need to rely on your understanding of just plain binary and plain hexadecimals. Okay, so we're gonna learn how to play with them, but I assume I'm just gonna review it very quick. I assume that you already know it. Okay, so just keep in mind that in binary you only have 2 symbols, and octal you have 8. This is heavily used in networking. And decimal, you have 10 symbols right here. If you count them, they have 10 symbols. That's why we call it the decimal base here, the binary base, because it's two symbols. And hexadecimal, we have 16 from 0 to F. So you know this is 10, 11, 12, 13, 14, and 15. So we have 16 symbols in there. All right. So knowing this is going to be very handy later on, because knowing the base is a core thing. All right. So what is the point of knowing binary numbers is we need to do integers, right? We need to represent numbers. So when we represent numbers, our numbers in real world, in the real world, they're going to be either integer or floating point. These are what the numbers are, right? Integer or floating points. We are not going to focus on the floating points right now. It's going to be at the end of the semester. From now onward, we're going to focus on the integers. So when we're talking about integers, we can see that the integers can be 1 or it can be -1, right? So this is what we call sign and unsign, okay? Unsign and sign. Okay, so we will understand what is sign and what's unsigned and how that is going to really, why those are very important. We'll understand later. If you give me a byte, which is what? 1, 2, 3, 4, 5, 6, 7, 8. This is 8 bits, right? 1 byte. And you want me to represent an integer number, I have to know whether I need to use this bit for the sign or not. If the number is unsigned, that means greater than or equal to 0. So I don't care about this bit. So numbers are always positive. Okay, so that is when I'm dealing with the unsigned. I don't care about this bit. I will use it as part of the system. But if I care about the signed numbers, that means it's going to be the range is going to include the negative. So it's going to be less than or equal to 0, right? So if you're going to consider this range, then you're going to have -1, -2, and so on and so forth. So we have to use this bit for the sign. So that's when we're going to deal with the sign numbers. Okay, and that's going to affect the range and everything. All right, so we're going to talk about that in a minute. And one more thing that you need to know about x86, okay, or int of x86, there is no -0. But in real life, we have a -0, right? So we always have what? Just 0. No negative, no positive. Just 0. That's it. Okay? I'll explain that in more details later. Okay, so this is what I talked about right now. So if you count the bits right here, 1, 2, 3, 4, 5, 6, 7, 8, that is the first byte. And this 1, 2, 3, 4, 5, 6, 7, 8, that's the second byte. So this is like 16-bit computer, okay? So if you look at the bit right here, this is what you call most significant bit. That's actually stands for the sign. Here is the least significant bit. That is going to be the one in the bottom. This is very important for shifting, but this is very important for the sign. And these are the bit numbering. So you start numbering from right to left. This is very important. I know English is your first language, and you do things left to right. So you have to change this habit, because in Intel, we are actually we're going to go all the time right to left. So keep that in mind, please. Okay. So this is like a byte right here. And if you look at this number right here, we have it all ones, right? So this is 1 byte. What if I have 1, 0, 0, 0, 0, 0, 0, 0? So this is just 1. How did I know that this is a 1? 2 to the power 0 is what? 1. 2 to the power 1. So 2 to the power 0 here is going to be 1, right? 2 to the power 1 is going to be 2. 2 to the power 2, 4. To the power 3, 8. To the power 4, 16. To the power 5, 32. 64, 128. Okay, did I miss something? I think so. This is 2, 4, 8, 16, 32, 64, and 128. No, I did not. Okay, so this is good. So you have this number. So if I know that this is going to be 1, right, guys? So this is a system that, I don't know if you like it, you can use it, but I use all the time to represent numbers. So if you say, okay, can you represent 22? So I would say 22. So 22 is going to happen by adding what? 16 plus 4 is going to be 20, and 2 is going to be 22, right? So if you want to do this right here, we're just going to say this is 0. We did not use it. We used this bit, right? So this is going to be 1, right? And we use this bit. That's going to be 1. We did not use 8. It remains 0. We use 16. It is going to be 1, and these are all zeros. So this is, in fact, 22 in decimal, right? You just add them up. You add 2 to 4 is going to be 6, and you add it to 16 is going to be 22. Okay? If you want to say, how about if I want to create, let's say 96. 96 is straightforward. This is 0. This is 1. This is 1. This is 0, 0, 0, 0, 0. So this is 64 plus 32 is going to be what? 96. right? So this is the way you're going to create the numbers. So the maximum you're going to create in here is what? That depends on, are you dealing with signed or unsigned, right? We're dealing with integer right here. We're dealing with the unsigned. If you add 1 to 2 to 4 to 8 and so on and so forth, you're going to get what? 255, right? Am I right? If you add 1 to 2 to 4 to 8 to 16, you added all of them together, you should get 255, right? That is going to be that's going to be the maximum number that you're going to store in this. So in fact, the whole idea right here is going to be 256, but since we are starting from 0, so you're going to go from 0 to 255. Okay, so 0, 0, 0, 0, 0, 0. If we have here 0, 0, 0, 0, 0, 0, 0, 0, that's 0. And we can have 1 and we can have 2. The maximum we can do is 255. What happens if we add 1 to 255? We're going to have 256, right? So that's beyond what this byte can handle, right? So that's when we're going to have an overflow. We're going to talk about that in more details. But now you understand that if I give you a space, you have to ask me what is the space. The minimum space is going to be 8-bit, which is a byte. If you give me an 8-bit, I would say 2 to the power 8 is going to be 256. Right? So you can store 250 things in here. Since I'm dealing with integers, right? I'm dealing with integers. I want to store 0, 1, 2, and so on and so forth until 255. If you count these, they're going to be 256 things that you can represent. That thing in our case is, it happens to be what? It happens to be integers. Okay? So this is going to be very, very important. Okay, so I believe that you know how to do this, you know how to translate numbers. So if you give me this number in decimal, I can use my own method. I can say 1, 2, 4, 8. So this is 8 plus 1 is 9, so I will know it's 9. You can use this method to translate. Or you can use this formula. And yeah, I believe that you already know how to use that, or you already learned how to use that in Introduction to Computing. If you said for some reason I don't, then I don't know, something is wrong. I don't know, maybe you were absent, maybe, I don't know, but it's a core component of Introduction to Computing. All right, so you need to revise that anyway. Okay, so if you look at the 37 right here, if you look at it, 1, 2, 4, 8, 16, and 32. So we have 32 active, we will take it, and we have 4 active plus 32, and we have 1. So 4 plus 2 is 6, and 6 plus 1 is going to be 7, and that's going to be 3. So this is 37. So I can figure it out without even looking at this number. Okay, so this is very important. So this is again how to translate. We are dealing with what now? With the unsigned. So when we say with the unsigned, we can go from 0, when we say the unsigned, to 255. Just keep that in mind, because if you remember, the bit that we have at the end in here, it is not being taken off for the sign, because we don't care about the sign. The numbers are either 0 or more. Okay, so in our case, more, it's not infinity, right? We cannot say infinity because the computer is a deterministic machine. So it's the more right here is defined. This infinity is defined by the number of the bits. So the number of the bits says you can go up to 255. Okay. So once we know how to, what's a binary, how to convert, what's a byte, what's the sign, okay, what's the unsigned. Now let's just look at adding binary numbers, okay? So if you look at how to add binary numbers right here, it is gonna be very handy, right? So if you have this number, which happened to be 4, you can use the method again, 1, 2, 4, 8. We don't need to go because these are all zeros, so they are meaningless. So we add what? These are not active. This is the only bit active. So that's correct. That's 4. This is again 1, 2, 4. So 4 plus 2 plus 1, it's 7. So that's correct, 7. Okay. So if you add 0 to 1, so you need to understand if you add 0 to 1, you're going to have 1, right? And if you add 1 to 1, you're going to have 0 and a carry 1. Keep that in mind. Okay. And if you have 1 plus 1 plus 1, you're going to have 1 and the carry 1. So how that happens right here, if you break this one down, it's going to be first, the computers always add 2 numbers. So this one is going to be first, 1 plus 1 is going to be 0 and the carry 1. Then we're going to take this number here, right? So 0 plus 1, 1, and we have a carry. That's why we said 1 and the carry 1. So you need to understand that as well, all right? So if you look at that right here, so we had 0 to 1, 1, 0 to 1, 1, 1 to 1, that is going to be 0, and the carry 1. We add 1 to 0 is going to be 1, 1 to 0 is going to be 1, and everything else 0 plus 0, 0 plus 0. So this is byte addition. We are adding 8 bits, which is a byte, and we have a carry right here. Okay, so these are the bit positions. So if you look at it right here, this is our 1, 2, 4, 8, right? So 8 plus 2 is 10, plus 1 is 11, and the result is 11. So even in decimal right here, this is going to be 11, and in binary is going to be 11 as well. Okay, so we are dealing with the unsigned integer, and that is very important for you to understand. And we focus mainly on x86 and the byte so far, but you also can have a word, d-word, quad word, and double word. So the more size you have, the more ranges that you can represent. If I just give you an 8 bits, then you're going to say 2 to the power 8. That's going to be what? 256. If I give you 16, 2 to the power 16, that is going to give you more, right? 2 to the power 16 is going to be 32,000 something. If I give you 32, 2 to the power 32 is going to give you 4 billion. 64 is going to go up and up, so you can represent more numbers, okay? Back in the days, we only can add things up to 255 if it's unsigned. So we have to think about how to extend the range. So we extended the space of the storage space because this represents storage. Do you see it here? You give me 16 bits, 2 bytes, then I can do more integer additions or subtractions. So just keep that in mind. This is something I assume you already know. So this is 2 to the power 0, 2 to the power 8 minus 1. Okay, so that is what I say 255. Because you're going to get the 0, right? 0 is part of it. 0 from 0 to 2 to the power 8, it's going to be 256 minus 1, 255. So if you give you a byte, you can do from 0 to 255. And if I give you 16, it's going to be the same. Okay, so it's going to be a 16 bits. Okay, that's going to be 32 things that you can represent, 4 billion, and so on and so forth. Okay, so we don't have 4 bits a computer or 2 bits computer. We only have 8 bits, that's for x86. Sometimes I create my own computer and I said, okay, your computer is of 4 bits, that's fine. So 2 to the power 4, you're gonna represent 16 things, but that's not a real machine. This is a real machine. It starts from 8 bits, which is a byte. This is a half byte. It used to be there back in the days, but no more. Okay, so if you have this part right here, which is 16 bits, and if it's unsigned integer, then you can do from 0 to 50. 15 means 1, 1, 1, 1. And if you take it 1, 2, 4, 8, 8 plus 4, 12. 12 plus 2, sorry, 14. 14 plus 1 is 15. So the maximum you can do is 15. The minimum you can do is what? 0, 0, 0, 0. So anything in between you can do in here. Okay? So that is just if your computer is a 4-bit computer, but that's not an x86 computer. Okay? So what is the largest number? Unsigned integer number for 2 to the power 20. So try to play with that, see what it is, and try to find the range. Okay, try to find the range using this formula because it's important to know the range. If you give me 4 bits, I know the range, that's my range. If you give me 8 bits, I know my range. My range is gonna be 0 to 225 here. I know my range. Okay, so you need to master this, okay? Giving you a space, like 8 bits or a byte, a type, right here we call it, then you're gonna give me the range, okay? And this is the hexadecimal. So why we need a hexadecimal system? It is straightforward, right, guys? So we say 1101, 1111, 0001, 1010, 0011. So this is a very long string of binaries, right, guys? So if we want to really make them easy to read, because this number is really large, we need to use the hexadecimal because the hexadecimal is reducing the long binary integers into a smaller one. Why that's important? Because when you need to address a memory usually has a size of 4 billion to more nowadays for terabytes. And if you want to use the binaries, it's going to be really long string. You cannot even present it in a debugger or in a software. So you have to reduce that length using a hexadecimal system. So that's why hexadecimal is heavily used in in languages like assembly, and once you get very close to the hardware, you're going to see hexadecimal a lot. Hexadecimal is a 16 symbol, right, guys? You got that already, right? If you have 16 symbols from 0 to F, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you're going to have A, so this is 0, right? 7. And then you're going to have 8, 9, and then you're going to start having what? A, B, C, D, E, F. You see it? This is which is in decimal 10, 11, 12, 13, 14, and 15. Okay? And you notice that the hexadecimal is going to be represented by what? 4 binary right here. So this is 8. Why 4? Why hexadecimal is represented by 4? Because 2 to the power 4 is going to be what? 16. Isn't that what we need? Because we have 16 symbols if you count them, right, guys? If you start from 0 here, these are 16 symbols from 0 to 15, right? To F. So if you count them in terms of symbols, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you have 16 symbols. So that's why, because you're going to represent anything and hexadecimal just using 4 bits right here. So if you want to say 0, 0, 0, 0, that is 0, 0, 0, 0, 1, that is 1, 0, 0, 1, 0, that's 2, 0, 1, sorry, 0, 0, 1, 1, that's 3, 0, 1, 0, 0, that's 4, 0, 1, 0, 1, that's 5. You see what I'm talking about, guys? So this is going to be 0, 1, 1, 0, 6, and this is going to be 0, 1, 1, 1, 7, and this is going to be 1, 0, 0, 0, 8. So you're going to go until you go to 1, 1, 1, 1, which is F, the one that you see right here. So after that, that's you're out of range. So your range is going to go from 0 to 1, 1, 1, 1. Okay? So that's very important for you to understand. All right, guys? So let me see. So that is the hexadecimal. You need to know why it is 16, because it's 2 to the power 4. Keep that in mind. So if you look at this number, since it's 4, I can divide the string by 4. And then I'll figure out what every group of 4 represents. So this is 1, 2, 4, 8. Again, this is 12, 13. So what is 13? 13 is D. So this is D. What is this? This is 1, 1, 1, 1, 1. So 1 plus 2, 8 plus 4 is 12, 14, and 1 is 18, right? 15, I'm sorry. So this is going to be F. This is 1, 0, 0, 0. This is 1, 2, 4, 8 again. So this is just 1. This is 1, 2, 4, 8, right? So 8 plus 2 is 10. So what's 10? 8. If you look at it, it's here. And this is going to be 1, 2, 4, 8. So this is 1 plus 2 is 3. So this number now is going to be D. F1A3. It's easy to read, right? Than just looking at this very long string. Okay? So this is what I explained right now. If you see a long string like this one, just going to divide it by 4 and use the rule of 1, 2, 4, 8, or use the whatever the rule that you feel comfortable with to convert from binary to a hexadecimal. This is the system that I assume that you know, to convert from hexadecimal to decimal. And this is like something I assume you already know how to do, so I'm not going to spend a lot of time on this. I'm just going to move ahead and try to look at the hexadecimal addition. Okay, so now we know how to do binary additions. We already did that. If you have 1, 1, 0, 1, 1, 0, 1, 1, so 1 and a 1, 0 and a 1, 1 and a 1, 0 and a 1, 1 and a 1, 0 and a 1, 1 plus 1 plus 1, we have 1 and carry 1. If we see a carry, that means we are out of range. We'll cover that in details later, okay? But right now, instead of doing this binary, we want to look at what happens if we add hexadecimals, right? Okay, so if you look at the hexadecimals right here, the numbers that we have right here, we're going to have A plus B. So what's A plus B? So we know A is what? 10, right? I'm sorry. And we know B is what? 11, right? So if we add this to this, this is going to be what? 21, right? Right, guys? Do we have a 21 in the hexadecimal system? No, we have from 0 to 15, right? So We don't have a 21, but why the result is 2 right here. So there are two ways to do this. Okay, so one way that you can follow, which is already in the book, the steps and everything. And this is what I call, what they call modular arithmetic. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Okay, so now we are at A, right, which is 10, and we have to go 11, right? So if we go 11, we're going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Interesting. So we have 5. But why we have the carry 1 here? Because we started from here, right? And then we now starting for the next time to get to the circle. So once we cross the F, we have to have a carry. Okay, I'll explain that in more details, but that's going to be very handy. You have this system in your cheat sheet and you're good to go. So 1 plus 6 is 7. 7 plus 4 is going to be 11. We have B, so that's not an issue. 8 plus 8. Why it's 8 plus 8 is 0? Because we don't have 16, right? 8 plus 8, it should be 16. But we don't have 16 in this range. It's like in decimal, guys, when we say 9 plus 1. Do we have 10? No, we're going to say 0 and the carry 1. That's why we call it 10, right? Because the symbols are 0 to 9. We don't have 10, right? The same, we don't have 16 in here. So if we say 8 plus 8, let's do the same rule right here. So if you are at this 8 right now and you want to go 8 times, so you're going to say 1, starting from here, 1, 2, 3, 4, 5, 6, 7, 8. So the result is 0 and the carry 1. Why? Because we crossed the F. If we stopped at the F, the result is F, but we crossed it. Then we have 0 and the carry 1. So 1 plus 2 is 3. 3 plus 5 is going to be what? It's going to be 8. Okay? This is straightforward. 13 is going to be D. This is 6. And this is what? This is 8. And this is 7. You see what I'm talking about? So what if I say, what is F plus F? Right? So you're going to say F plus F. It should be what? 15 plus 15, right? 15 plus 15 is going to be 30, right? We don't have 30 in this range, right, guys? That is our range. We don't have the 30 in this range. So what we're going to do, so we are at F right now, and then we're going to go what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we're going to have E and a carry 1. Why carry 1? Because we crossed the F when we start counting. We say 1, 2, 3, 4, and so on. So it's going to be E and a carry 1. Okay, so if this is the maximum you can do, I mean, that is the best. You're always going to have a carry of 1, no matter what. Okay, guys? So this is also subtraction. Subtraction is very, very interesting also in hexadecimal. So you need to understand how to do subtraction in hexadecimal. So in hexadecimal right here, we're going to have 5 and 7, right? If you want to subtract 47 from 75 or A2 from C6, okay? Let's look at this right here. So before I do this, I just want to explain that in decimal because you guys are very comfortable with decimal. So let's say in decimal, if we have, let's say 27 and 19, right? If we want to subtract this from this, it's not going to happen, right, guys? Because 7 is smaller than 9. So we borrow 1 from here. If you borrow 1, it's going to be 17. In fact, we are not borrowing 1. Since this is a decimal system, we are borrowing 10. 10 plus 7 is going to be what? 17. But for simplicity, they just taught us, the mechanics, just going to be 1 right away in here. And then they're going to say 17. It's not 1, it's 10. Always borrow 10, right? So that's going to be 17, right? So, and then this becomes 1, right? Because we already take a 1 out of there. So 17 from 9, it's going to be what? It's going to be 8. 1 from 1 is going to be 0. Okay, guys? So the same happens in here, but since the hexadecimal, the base is 16. So if this is smaller, then we have to borrow 16, right? Plus 5, right? And then this is going to be 1. It's going to be 21, correct? So if this is 16 plus 5 is going to be 21. That's what we borrow. Then 7 from 21 is going to be what? Right? So what is it? Is it going to be 14, right? Is it? Yes, it is. It's 14. So we don't have 14 in hexadecimal. We have E. So that's why you see the E right here. Since we take 1 from here, like the one we take it from here, so it's going to become 6. So 6 from 4 is going to be what? 2. And then here is going to be the same. Okay, so you can play with those as an exercise. You can see more exercise maybe in the lab as well. So you can say, let's say, let's say 72, and you're going to say maybe A1, and try to do that. Okay, try to borrow and see what happened. All right, so this is the subtraction. Okay, and now we're going to move into a very important part, which is a core part for me. This is more important than anything else, which is the sign and assign. Since I've been here for quite some time, I will give you some time to digest this, and then I will go on and release the second video just in a minute. And that the second video, we're going to cover the 2's complements. Okay, so the 2's complements is going to be mainly talking about sign and the unsigned. All right, so I will let you go for a while, and then I'll come back and I'm going to finish the rest of it. All right, thank you for now, and then we're going to be back just in a second. Thank you.